Now let's first look at the exercise 6.3. We ask you to figure out what is the output given the input. The transfer function are given as the figure 6.4. The left-hand side is the magnitude, the right-hand side is for the phase angle. If you are given the input, you can see our input in fact has 3 different components. So we are going to determine one by one. For the first one is 1. Then you know that the frequency is 0. So you look at what the transfer function for the frequency equal to 0. Here, as this frequency equal to 0 is at this origin point, you can see at frequency equal to 0, the magnitude equal to 4, and then the phase angle equal to 0. So the transfer function is 4, 0. The magnitude is 4, the phase angle is 0. Then we multiply by 1, you're going to have the 4, and the phase angle is 0. So you can just write down a 4 there. So it will be 4. I don't know why I cannot input a 4 here. Okay, so the first component after the transfer function, the output will be 4. Now let's look at the second one. The second component is 2 cosine 2000 pi t. So the magnitude is 2 and the phase angle equal to 0. The frequency, we know that inside this parentheses is omega t. So omega equal to 2000 pi. Then the frequency will be 1000. Then we look at the 1000. You can see for the 1000, the magnitude is 3. So here you can see the magnitude is 3. The magnitude multiplied by magnitude, you're going to get a 6. So it will be the 6. The magnitude will be the 6. Then look at the phase angle. If the frequency is 1000, you can see the phase angle will be 30 degrees. And for the previous component, the input component, you don't have the phase angle. After the transfer function, you have a phase angle of 30 degrees, so that we know it should be we won't change the frequency, so it's still 2000. Pi t plus 30 degrees. This is the second component. Now let's look at the last component. For the last component, we first identify the magnitude, which is 3, and then the phase angle is 0. Then we look at the frequency. Inside the parentheses is omega t, so omega equal to 6000 pi. Then frequency will be equal to 3000. Then let's look at the 3000. Frequency equal to 3000, the magnitude equal to 0. Then we know that if you multiply by a 0, you won't have any value there. So the third component will be filtered out. You no longer have the third component because the magnitude will be equal to 0. But if you want to look at for the frequency equal to 3000, what will be the phase angle? You can look at the phase angle graph. For the frequency equal to 3000, then you're going to get this like 90 degree here. This is how we figure out what is the output if you are given the input and the transfer function. We know the output will be equal to the input multiplied by the transfer function. Then based on the magnitude graph and the phase angle graph, you identify the frequency. For different frequency, the frequency response will be different. So you figure out what will be the magnitude and the phase angle for that frequency, then figure out what is the output for that component. That is the first question. The second question is for the exercise 6.5. So if we have an input signal, it's given like this, then you can see we ask you to figure out what will be the output. This question is pretty much the same as the previous question, the exercise 6.3, the questions we've just done. You are given the input signal, different component of the input signal. Then you identify based on the frequency for each of the component, what will be the output, because the frequency response is different for different frequency. Then you add them up, you will get the final output. The difference of this question with the previous question is, previous question, the transfer function is quite simple. You just have the straight line for the magnitude and the straight line for the phase angle. But if we have a real circuit, the filter circuit, then in fact we have the curve to represent the magnitude plot and the phase angle plot. You won't have the direct straight line. Then we need to figure out what is the magnitude and what is the phase angle. Since we are given the circuit like this, the resistor and the capacitor connect in a series circuit, and then we get the output from the capacitor. We know this is a low-pass filter. So you figure out what will be the transfer function for the low-pass filter. Then for the low-pass filter, the transfer function for the magnitude HF equal to 1 over square root of 1 plus F over FB square. And the phase angle is equal to negative arctangent F over FB. We are going to base on these two formula to do our calculation so that we can figure out what will be the output. First, you need to figure out what is your FB, what is the break frequency. After we given the resistance and the capacitance, we know the FB is 1 over 2 pi RC. So you can figure out what is this break frequency. Then for each of the component, we are going to identify what is the frequency for each of the component. Then depends on that component, we use the magnitude formula and the phase angle formula. Then we can out what is the frequency response for that component. I shared the file, the solution for exercise 6.5. Don't know if you guys can see that. So first, we will identify the break frequency, FB equal to 1 over 2 pi RC. We plug in the resistance and the capacitance so that we know the break frequency will be 200. This won't change. This depends on your circuit. After you set up your circuit, what is the resistor, what is the capacitor, then your FB won't change. This is a constant. Then for each of the component, we have 3 components here, 10 cosine 40 pi t, 5 cosine 1000 pi t and 5 cosine 2 pi 10 to the power of 4 t. So these are three different components. We are going to identify their frequency first, then figure out what are the magnitude and phase angle for that frequency, so that we know what will be the component for the output. Let's first look at the 10 cosine 40 pi t. That is the first component. We know that the frequency will be 20 Hz because 40 pi is omega. Omega equal to 2 pi f, so f equal to 20 Hz. Then for the input, the phase angle equal to 0. The input, if we want to write in phasor representation, is 10, 0. Then we calculate the magnitude for frequency equal to 20. Note that this frequency is a variable, depends on your component. After you given the component, you will know the frequency. So if your component is cosine 40 pi t, your frequency is 20. So here this f is 20. Then we plug in the formula. The magnitude equal to 1 over square root of 1 plus f over fb. So we plug in the values. The frequency is 20. The fb, the break frequency, is 200. This won't change. We plug in the values and then we calculate the magnitude is 0.995. So here you can see this is the magnitude change. Your input will multiply by this change, then you will get your output. This is the magnitude for the transfer function. This magnitude equal to 0.995, that is quite close to 1. So that means your output is pretty much the same as your input with respect to the magnitude. Then let's look at the phase angle. For the phase angle at frequency equal to 20, we know the formula is negative arctangent f over fb. So we plug in the value, f equal to 20, frequency equal to 200. You plug in this value and then you get the phase angle equal to negative 5.71. So that is our phase angle change. Then we know since we have an input, use 10, 0, the phasor to represent our input, then we know that our output will be the input multiplied by the transfer function. The transfer function's magnitude is 0.995 and the phase angle is negative 571. Then you multiply by your input, you are going to get the output. Magnitude multiplied by magnitude. We have input magnitude is 10 multiplied by 0.995. We are going to get 9.95. And for the phase angle, we add them up. The input phase angle is 0. Add the negative 5.71. We are going to get the negative 5.71. So that is the output for the first input in the phasor representation. Now let's look at the second component, 5 cosine 1000 pi t. We first identify the frequency. 1/3 pi is omega, so the frequency equal to 500 Hz. And the input using the phasor representation is 50. We calculate the magnitude for transfer function at frequency equal to 500, equal to 1 over square root of 1 plus f over fb squared. We put in the values. F, the frequency now is 500 Hz. So we put 500 for F. And the break frequency is 200. Note that this won't change. And we calculate the magnitude is 0.371. So this magnitude is very small. It's less than the 0.707. Means we think for this signal, at the frequency equal to 500, this signal will be filtered out because the magnitude is only about 37% of your original input. So this signal, most of this signal will be lost. We figure out this signal. For the phase angle at frequency equal to 500, we use the same formula, negative arctangent F over FB. Plug in F equal to 500, FB equal to 200, we will get the phase angle as negative 68.2. Your input is 50. Output will be the input multiplied by the transfer function. The transfer function's magnitude is 0.371, and the phase angle is negative 68.2. Input signal's magnitude is 5 multiplied by the transfer function's magnitude 0.37. We get 1.86. You can see this output signal is much less than 5. 1.86 is much less than 5, so this signal will be reduced a lot. It cannot be filtered out. The phase angle is negative 6.2. Let's look at the third component. The third component is 5 cosine 2 pi 10 to the power 4t. This frequency is much higher. We know 2 pi 10 to the power of 4 is omega, so frequency is 10 to the power of 4 Hertz. This frequency is very high. As we said, usually we think that the low frequency are the signals, the high frequency are the noises, most of the case. So we know that these most probably are the noises, and we are using the low pass filter. We get the output from the capacitor. So we can predict that the magnitude for this component will be very small after the transfer function, and the magnitude for the transfer function will be very small. We use 50 to represent the input. Let's look at the magnitude if our frequency is 10 to the power of 4. We plug in the formula to calculate the magnitude of the transfer function, 1 over square root of 1 plus F over FB. F now is 10 to the power of 4. FB is 200. Now you can see at the bottom, the value is much higher. Then we get the magnitude is 0.019. So you can see this magnitude is very small for the transfer function. And for the phase angle, F at frequency at 10 to the power of 4 is negative arctangent F over FB, 10 to the power of 4 over 200. We get the phase angle as negative 88.9. Then our input is 50. The output is input multiplied by the transfer function. Magnitude, you can see transfer function's magnitude is very small. Multiplied by the magnitude of 5, the input, we get 0.1. You can see the output magnitude is very small. This signal, you can just think that is reduced almost to 0. For the phase angle, the transfer function is negative 88.9. The input is 0. We add them up, we get 88.9. So this is the output for the third component. Then we know that if we want to figure out what is the all output, we need to add these three components up. This first formula is phasor representation. It is what we just got from the previous calculation. Since we need to know what will be the signal of your output, we need to convert them to the cosine. Note that you won't change the frequency. Previous, what are their frequency? You won't change. Now the first component still 40 pi t. You won't change this 40 pi. You cannot change the frequency. Just depends on this frequency. The magnitude will change. The phase angle will change, but your frequency won't change. So still 40 pi t here, but the magnitude changed to 9.95. And the phase angle changed to negative 571. Then for the second component, the frequency won't change, still 1000 pi t, but the magnitude changed to 1.86, and the phase angle changed to negative 68.2. Then the third component, the frequency won't change, still 2 pi 10 to the power of 4t, but the magnitude changed to 0.1 and the phase angle changed to negative 88.9. Through this calculation, you can see that for different frequencies, their response will be different. Since this is the low-pass filter, then for the lower frequency, the signal can pass through. We can see the magnitude of the transfer function is 0.995, very close to 1. But if you continue to increase the frequency, if your frequency is higher, like 500 Hertz, then your magnitude of the transfer function will be 37% of your input. So the output will be reduced a lot from the input. Then if your frequency is very high, then the magnitude is quite close to 0. So here you can see the output magnitude is 0.1. It's very small. Now let's look at the last question. For the last question, it asks us to sketch the approximate straight line body magnitude and the phase plot. So we know that if you are asked to figure out what is the body plot magnitude and the phase plot, the first thing you need to know is to identify what is the filter, what type of the filter. For this circuit, we get the output from the capacitor, so that you know this in fact is a low-pass filter. If we get the output from the resistor, that will be the high-pass filter. This is for the RC filters. For the RL filter, for the resistor and the inductor connect in series circuit, that is also a filter. If you get the output from the inductor, you will have a high-pass filter. If you get the output from the resistor, you will get the low-pass filter. The RC filter and the RL filter are duality here. If you get the capacitor's output, that is the low pass. But if you get the output from the inductor, that is the high pass. So that is the duality. No matter if it is RC filter or RL filter, the most important thing is to identify what type. Are these a high pass or are these a low pass? Then you know the straight line body plot will be different for the low pass and the high pass filter. In this case, we get the output from the capacitor so that we know this is a low pass filter, right? Then after you figure out this is a low pass filter, you need to figure out what is the break frequency. So for the break frequency, in this case, we know that for the break frequency is equal to 1 over 2 pi f. 1 over 2 pi RC. The break frequency equal to 1 over 2 pi RC. So you plug in the values 1 over 2 pi and then multiply by the R, which is 500 over 2 pi, then multiply by this 10 to the negative 6, this is 10 microfarad. Then the frequency, you will do the calculation, it will be 1000 Hertz. This is our break frequency. The FB, the break frequency is 1000 Hertz. Then based on this break frequency, we can figure out what is the body plot. Let me move this to one page so that we can see it clearly. So I just briefly draw the body plot. Then you guys can can do some practice by yourself so that you will know how to draw the body plot. After you figure out the break frequency, you put it in the middle at your range. So let's say this is our range for the frequency. Then we put this as the middle, or break frequency as the middle. So this is going to be 1. Sorry, I cannot put it here. So this is 1000 Hertz here. Then we know that if the frequency is less than this break frequency, then it will be equal to 0. So you can draw a line. If it is less than the break frequency, then all this part will be equal to 0. Then if it is higher than the break frequency, then for each of the decade, it's going to be reduced by 20 dB. So here you can see this is another decade. Let me seems I have some trouble to draw the. Okay, so this is the next decade. And let me draw another one. This is the previous decade. So this is 10 F 10 times F. So here, this is the 10 times of FB. This is FB. This is FB divided by 10. Now, each of these decades, I just draw like this to give you guys an idea. You can make it more look better. You add these decades here so that you know what will be the values for each of these critical points. Now, this critical point, the first one is the break frequency. If the frequency is less than this break frequency, or the magnitude in dB, note that I didn't draw this part, but okay, let me see. So the y-axis is the magnitude of the transfer function in dB. So this is our magnitude of the transfer function. Note that it is in dB, the decibel. Then the x-axis is the frequency. Then for the roll-off, that is the slope of this part when the frequency is higher than the break frequency. For each of the decade is going to be reduced by 20 dB. So here you can see this is the next decade, 10 to the 10 multiplied by FB. So here at this point, this will be your negative 20 dB. So this is a negative 20 dB. For this decade, each of the decade is going to reduce by 20 dB. So this slope is each decade reduced by 20 dB. So this is for the magnitude plot. For the phase angle plot is almost the same. Okay, let me just change directly here. So if we want to draw the body plot for the magnitude, for the phase angle, it is the same thing. We are going to identify the break frequency first. So you will get the FB and put the break frequency as the middle of your range. So let me see, this is the phase angle. Then you know that for the phase angle, for the low pass filter, when the frequency equal to FB, we know that we calculate the phase angle using negative arctangent F over FB. So if frequency equal to FB, then we know we are going to get a negative 45 degree. So this will be a negative 45. Let's see, this is negative 45. That is when you have your FB, the frequency equal to FB, you're going to get a negative 45. Then we know that if the frequency is much less, the frequency is less or equal to FB divided by 10, that is quite small, then your phase angle in fact equal to 0, because we know that the phase angle is arc tangent F over FB. If F is quite small, then F over FB is close to 0. So the phase angle is close to 0. If your frequency is less than FB over 10, we can just think that it is 0. So we can draw a line. For less than the tenth of the FB, it is equal to 0. So this is all this part. Then if the frequency is higher, we know that the arctangent, negative arctangent F over FB, if frequency is much higher, then F over FB is much bigger. You can think that as infinity. Then we know that we are going to get a negative 90 degree. Then if the frequency is much higher, let's see, this is negative 90 degree. If the frequency is much higher, is higher than 10 to the 10 multiplied by FB, we know they all should be negative 90. Then between the F over FB and 10 FB, we know it will be the straight line. So you just connect these 2 point, you are going to get the body plot for the phase angle. When your frequency equal to FB, you will get the negative 45. When the frequency is less than FB over 10, you will get 0. And when the frequency is higher, like 10 multiplied by FB, your phase angle will be negative 90 degrees. So this is how we draw the body plot for the magnitude and for the phase angle.